Special polynomial products. We'll be looking at perfect square trinomials and the difference of two squares. Here we're asked to square the binomials that are given and then look for a pattern and generalize a rule for the quantity a plus b squared. So let's start by squaring the expression that's given, multiplying it by itself. Now we'll use the double distributive property. We'll combine the two middle terms, and we'll do the same thing for the second example. We'll square it out, combine the middle terms. Okay, so now to generalize a rule for a plus b quantity squared, we'll look at our resulting trinomials in both cases and compare the three terms against the given binomials. So notice 2t, if you square that first term, results in 4t squared. Same thing in the other example, 4y, when you square it, is 16y squared. So it looks like the first term of our trinomial rule will be a squared. Now let's look at the second term. You square 2 and you get 4. You square 3 and you get 9. So the last term in our trinomial will be plus b squared. Now there's going to be a middle term. So look at it in the trinomial, the 8t. How does that relate to the two terms in the binomial? Look at the 24y. How does that relate to the two terms of your binomial? Well, if I take my two terms, I multiply them together, and I double it, I'll get my middle term. So now I'm ready to generalize a rule. A plus b quantity squared equals the first term squared plus twice the product of a and b plus the last term squared. And I can use that rule instead of multiplying them out, instead of multiplying the binomials out longhand. Right, so let's do something similar for a minus b quantity squared. So t minus 5 quantity squared becomes t squared minus 10t plus 25. 2x minus 3 quantity squared becomes 4x squared minus 12x plus 9. To generalize a rule, we'll do the same thing. Look at your first term of your resulting trinomials. Where did that term come from in your original problem? Well, it's the square of the first term, right? Now let's look at your last term in your trinomial. It is the result of the second term squared. And the second term will have a negative sign, right? When you square a negative number, it becomes a positive. Now, this is true in both examples. So I will be able to generalize the first term and the last term of my rule. Now the middle term, let's think about that. If you multiply negative 5 times t, that's negative 5t in the first example. Negative 3 times 2x is negative 6x in the second example. And you double those products, you'll get the middle term of your resulting trinomial. So we've just made sense of where these trinomial terms come from. A minus b quantity squared is generalized as a squared minus 2ab plus b squared. Okay, one more style of problem to generalize. Notice these have a similar structure. It's a minus b times a plus b. Whether or not it's the subtraction sign comes first or second in the binomial does not matter, as long as there's one of each. So let's go ahead and multiply using double distributive in the first example. When we combine like terms, do you see the middle terms cancel out? We'll do the same thing in the second example. Middle terms cancel out. And so now we're asked to generalize a rule for a plus b times a minus b. So it looks like you're definitely going to be squaring the a in both examples. So it's safe to say that when we generalize the rule, the first thing we'll have is a squared. Now we're taking the -6 times +6, that's -36. Over here, +4 times -4 is -16. So we'll have minus b squared, because it's always going to be a minus sign following the a squared. So there's our rule. So the three examples we just did are classified as special polynomial products. The first two types are called a perfect square trinomial, because they're the product of a factor times itself. So when you have something, a trinomial, in the form a squared, or perfect square, plus 2ab plus b squared, we call that a perfect square trinomial. In the third example that we did together, that's called the difference of two squares, and you can see why, because a squared minus b squared, we're subtracting two perfect squares. All right, so let's use the generalized rule and get some practice squaring these binomials. In this first example, we are squaring a plus b quantity squared. So it's, in example A, it's the first term squared plus 2 times x times 2 plus the second term squared. And we're just going to simplify it and we're done. Let's do the same thing in the second example. Square the first term, multiply 2 times the product of both terms plus the last term squared. And now we simplify. Now we could have gotten these answers if we physically squared both binomials. This is just a little bit more efficient way to square binomials. Same thing when there's a minus sign between the two terms. We start with squaring the first, minus 2 times the first times the second, plus the second term squared. And we simplify it. In the second example, the first term squared will be 4x squared. The last term squared will be plus 49. And 2 times the two terms will be minus 28x. Right, so we had practice with those. Now let's get practice and see why in example A we end up with x squared minus 9. Because we're going to square the first term, we're going to square the second term, and there's a minus sign in between them. We got you started in example B. We square the 5x, we square the 4, and we end up with 25x squared minus 16. So using these three generalized rules, we have some practice problems for you. And if you want, you can pause the video and look back at the sample rules that we've given. And when you're ready, hit play, because the answers follow this slide. Okay, so here are your answers for these 6 problems. See how you did.